and welcome to Tinkering with Edkelar. In a previous video, from about a year ago, I restored an HP 1600A logic analyzer. Clearly one of the first of its kind, with an integrated oscilloscope screen to show rows of zeros and ones. It has a companion model, the 1607 here, that features the same analyzer but without the integrated scope part. Instead, you connect to the X, Y and optionally Z inputs of an existing scope. Another strange difference is that the 1607 here doesn't feature the map mode that the 1600 has. The logic board has the relevant ICs unpopulated and the display board is missing the decoding function for it. So, let's have a look. I want to bring this one up to the same level as the 1600. That means complete parts cleanup, lubrication and recapping. Let's hope that none of the chips are broken. Standard TTL chips in dip cases are getting rare. My unit arrived in pretty good condition. Only the handle came loose, but that must have been during transport, as there were no missing parts. Taking apart the device first. Funny enough, the transformer also shows some signs of moisture ingress, but nowhere near as much rust as the one in the 1600. It is a bit hard to disconnect the BNC connectors. The wires go through one PCB to the other and access to the pins on the PCB is kinda deadlocked. The two primary PCBs in this device are the display board, which creates the output for the scope, and the acquisition board, which handles the data input and storage. They are connected with a set of PCB connectors in this case. You can see the unpopulated chips for the map mode right here. Oddly enough, those are the same ones that were broken in my 1600 model. What are the odds? Recapping time! The main filter caps are screw-in types. I found compatible ones again. Most of the other electrolytics are tantalums again. Since I replaced them on the 1600, I also replaced them here. Axial ones are prohibitively expensive though, so I bent the droplet style ones to fit. The main power switch is almost stuck. It requires pulling on it to snap back. The usual disassembly and cleaning of old grease does the job, however. The push buttons are easy to disassemble. No desoldering required this time. USB probe pod sockets need some magic eraser. I take them apart for easier cleanup, but I keep the bottom part on the PCB. The pinout is crazy tiny. The two potentiometer knobs are both cracked. Plastic doesn't age well. I hope that some crazy glue will fix it. And after a good cleanup, it's assembly time! Fresh thermal paste for the heatsink. The power supply unit gets done first. It's a good opportunity to check the voltage outputs and turn down the 5-volt rail. Why turn down that one? The plus-minus 12-volt rails are simple linear regulators, but the 5-volt one has an adjustment and a crowbar section. The concept is simple. If the output voltage is larger than the Zener diode in here, 5.6 volts in this case, the triac will trigger and create a dead short across the 5-volt rail, which in turn will blow open the fuse. This is why any downstream chips are protected against overvoltage, especially if the regulator fails. Oh, and the diode in here does the same short for reversed voltages. So if by any chance during my fiddling with the 5-volt rail it got set too high, it's going to lead to a blown fuse. That's why I turn it down. Assembling the case is a careful step-by-step process. This design has screws nested between elements, so every step needs to be in the exact order. Also, replacing the bulb for the power indicator with an LED, just because. The circuit has a resistor for it already, so I just replaced that with a suitable value. no visible change required. And finally, after everything is connected again, I can turn it on. So far, so good. No smoke and the expected LEDs light up. Shame on the power LED though. I picked an orange one, which is disappointingly red though. I might change that eventually. To do the final adjustment for the clock timing circuitry and power supply, I need the probe pods connected. Good thing I still found a set on eBay. Now to set the 5-volt rail. There. And take a quick peek at the output signal. Nothing? That's not good. Neither horizontal nor vertical output shows anything. I can only adjust the DC offset with the center trimmer, and the size trimmer does shift that around too, so the output amplifiers seem to be working. I backtraced the problem and found out that there is nothing coming out of the DA converters that get used for the digital positioning. Also, the 100 kHz oscillator for the digits isn't oscillating. The plot thickens. When checking that oscillator as one of the easiest components, I found that Q3 did have negative 12 volts on one side, but instead of the plus 5 volts on the other, it had negative 0.8 volts. And that led me to checking the 5 volt rail. Oddly enough, most chips on the display board had it just right, but some had negative 0.8 volts instead. Odd. Now here's what I learned. The analog output signal part of the circuit has a distinct set of power rails. These are filtered via a 100 microhenry choke. I'd guess this is to prevent the analog signal from leaking back into the digital part, but that choke went bad, and it didn't carry the 5 volts across. The negative 0.8 volt I got must have leaked from the negative 12 volt rail over some of the components. My guess is Q1 and Q2. After replacing the failed one with a close enough one I had in stock, I finally got an output signal. Phew! Good thing nothing got fried. Now my digital scope has an XY mode, but in best tradition that's a pretty bad approximation only. One can somehow see the digits, but it's ugly. Let's downgrade a few generations. Now that's what I call bridging technologies. A logic analyzer with tubes. But at least it works. The blanking output, also known as the Z output, also works, but it's not useful for the tube scope. The beam mod input there needs high voltage negative pulses to turn off the beam, not a plus 12 volt one. And now the big question. Does the connection between the 1607 and 1600 work? First, the trigger bus connection. This essentially passes the trigger signal between the two devices and, depending on the selected trigger option, will either ignore or respect the trigger bus input. Second, the I/O interconnect. I checked the pinout of both ports and apparently a 1-to-1 connection cable is required. I made one, so let's give it a go. And nope. As soon as I connect that cable to the 1600, the display goes bonkers. Clearly, the cable is messing with some of the TTL levels. My homemade cable is not good enough. Sorry, I really wanted to show the two units together on the same screen, but it's not going to work like this. What's left? Again, a few little details. I found a proper HP interface cable for the I/O ports, which should arrive in a week or two. Second, all of the pods, except for the clock ones and one data pod, came without probe wires. I need to make some, so I can hook up the test units without duct tape. In that regard, does anyone know a good, affordable source for chip test clamps, especially for dip sockets? The one that I can find are almost $40 a piece, and I'd like several of them with different pin count. That adds up quickly. I only can find surface mount versions online, and I already have some of those. I will post updates as soon as I have something. For now, I hope you enjoyed this project. See you next time! That is a pretty bad approximation only. One can only...